Our topic today is surface area of pyramids and cones. And when we talk about pyramids, what we're talking about is any sort of two-dimensional figure. It could be a triangle or a square, hexagon, pentagon, any polygon. And we take the vertices of that, or the corners of whatever that figure is, and connect them to an apex, a point above the figure. So for example, if we had a square-based pyramid, we would start with a square, and then we would connect each vertex to an apex, to a point above that. Perhaps that's the point, and then we connect each of these vertices to that point, and we're left with a pyramid. Now, a right pyramid is a pyramid that apex is directly above the center. It's directly above the center of the polygon that's at the bottom. And when we're talking about surface area, all we have to do is add up the surfaces, the areas, the individual areas of the surfaces on the sides and on the base. So let's say, for sake of discussion, that we had this pyramid, and we said that this was 5 millimeters, and this was 5 millimeters, as I did say it was a square-based pyramid, and that the height of one of the faces, that's here, is 22 millimeters. Clearly not drawn to scale. Okay, what are we going to do? Well, we've got triangles all the way around. Each of those triangles, 5 millimeters across the bottom, and a height of 22. As we know, the area of a triangle is 1/2 of the base times the height. So in this case, 1/2 base times height gives me 1/2 of 5 times 22, which is 55. And it's in millimeters, millimeters squared, millimeters squared. The base is 5 times 5, that's 25. I have 4 of the triangles, so I'm going to multiply this times 4, and I get 220, and then I add the base, 25, and I get a total surface area of 245 millimeters squared. Now when we talk about cones, cones are the same idea, in the sense that you're taking something at the bottom and then having a point and connecting it. Of course, with a cone, what's the difference? The cone has a circle at the bottom rather than a polygon of some kind. So I actually want to do something a little bit three-dimensional with you today. And we're going to start with just a circle, okay? Just a circle. Now if I take that circle, and I'm just going to cut an angle out of that circle. So let's say I cut this circle here. I'm cutting right into the center, and then I'm also cutting right into the center along another line. Doesn't actually matter what angle you use. But if I then take, now of course I have a sector, and we can figure out what a sector, what the area of the sector is. We've done that before. But if I take this sector and I fold it, and I didn't bring tape, but you can imagine what I'm doing here. If I take that and I round it up and I just fold that edge together, then I have a cone. And I take another circle that's the size of the base, and I put that together, and then I have a cone of that size. Okay? And if you think about it, here's what's the important part from this visual is, the circle, you know how to get the area of the circle. Pi r squared, right? The radius of the circle. Now, how am I going to get the area of this thing? Well, the line around the outside is the same as the line of my circle. Okay? Remember, I make my cone this way. Whoops. I make my cone this way. And then that goes there, so they're the same. Okay? And the radius of this circle is the same thing as the height, or the slant height, of the cone. So we're going to talk about how to do that in just a second, but I wanted you to visualize it. Now, what if I were to change the shape of my sector? let's say for the sake of discussion, I took my scissors again and I cut another chunk out of it. Now, still a sector, yes, it's still a sector. But if I take this now and I put those together, what have I done? I just have a different shaped cone. The bottom is going to be the different size, so I have a different size circle that finishes up my cone, but still it's true that the circumference of the base is going to be the same as this outside curved distance of the sector. Now the question is, how do we figure that out? And here's what you need to think about. Let's say that I have a sector that I'm going to turn into a cone, and if you think about it this way, how did we figure out the area of a sector when we were doing that previously? We figured out what fraction of the circle it was, and then we took that fraction of the whole circle. So for example, in this one we might say, well, it's 3/4, roughly. It's 3/4 of the whole circle. This in here is 270 degrees. We would say 270 over 360, because those are the angles that are involved. But in our scenario, we don't have the angles to deal with, but we do know some other important information. So what you'll typically be given is the slant height of the cone. Remember, when I put the cone together like that, the slant height of the cone is the same as this radius of our sector. So we'll call that L. And what would the area of the whole circle be? The area of the whole circle would be, excuse me, not the area, the circumference of the whole circle would be 2 pi, and it would be L instead of R, because this is my radius. And what portion of it do I have? Well, we already figured that out. We would have figured that out from our circle that served as the base. It would be 2 pi R. Here's my circle over here. That is the base of this cone, and it has a radius of R and an area of a circumference rather, of 2 pi R. That is the circumference. That circumference is the same as this curved edge right here, this outside arc of my sector. So the fraction of the whole is going to be this fraction, 2 pi R. That's going to be the fraction of the whole. Now, how much is the whole? How much is the entire area here? Well, you know how to get the area of the circle. It's 2 pi R squared, but in this case it's, pi R squared, but in this case R is equal to L, so we multiply this times pi L squared. Now, let's get our circle out of the way just temporarily, so that it doesn't confuse our drawing here. We're just trying to figure out the area of this part of the cone, the surface area of the side, right? So now then, the beautiful thing about this is a lot of these numbers cancel. You know how to do this. The 2's cancel, the pi's cancel. Then we have, if we do this, we have pi L squared R over L on the bottom. One of the L's cancel, and this simplifies to pi L R, or pi RL, whichever way you prefer to write it. That's going to give us, that little equation is going to give us the curved area of my cone. But I also need the base. And as we said before, then I'm going to have a base, and that base has a radius of R, the same R as this R over here. And we know that the area, not the circumference, but the area of this is pi R squared. And what that means is, whenever I'm trying to figure out the surface area of a cone, the base plus the slanted part, then that area is pi R squared plus pi RL, or pi LR. So I'm just going to rewrite that here, so we have it easily to work with. Pi R squared plus pi, I'm going to write LR. R. So, let's try an example. Let's say we have a cone with a radius of 2 and a slant height of 4.5. So I have a cone with a radius of 2 and a slant height of 4.5. And that is in meters this time. All we have to do is plug it in here. What do we get? We get pi. What's r? It's 2. So 2 squared plus pi. L is 4.5. Oops. And again, r is 2. Now we can sort of simplify this a little bit. 2 squared is 4. It makes 4 pi. Plus 4.5 times 2 is 9. Times pi is 9 pi. Which of course simplifies to 13 pi. And that's the exact answer. So we can either have an exact answer or we can have a 2, 2, or 3, or 1, or whatever decimal places. So if I need the exact area, surface area, then I would have 13 pi meters squared. That's also approximately equal to what? That's approximately equal to, if I wanted to 2 decimal places, you could put that in your calculator and you would get 40.84 meters squared if we went to 2 decimal places. Now the other kind of problem that you will occasionally get in this situation is where you're given different information than this. So let's say we're going to redraw this. And it doesn't matter which direction the cone is turned. It could be an ice cream cone, could be a cone you wear on your head. Okay? Let's say that we have a cone. I'm going to draw it the other way this time. We have a cone shaped like this. And let's say that we know that the radius is 3 centimeters. 3 centimeters. And instead this time we're going to tell you in advance that the surface area of this curved part, not the top, just the curved part, that this area here, surface area, is equal to 100 centimeters squared. Now, from that, can you tell me what the slant height is? Certainly, you can figure that out, because we know, remember, this is the part, excuse me, where am I at here? This is the part that tells me what the surface area of that slanted part is. So we would say that it is the surface area of just this is equal to pi LR. We already know that the surface area is 100 pi. And then we know that, the length is what we want, so we have to figure that out. And R is equal to 3. Okay? Now we can do a little bit of algebra, which shouldn't be too hard for you. If these are multiplied and I want to move them to the other side, I just divide. So that would mean that 100 over 3 pi is equal to L. I've just divided both sides by 3 pi and put it over there and canceled it from the other side. And that should be sufficient. If I want an estimate to 1 decimal place, you could put this in your calculator and you'd find that it was roughly equal to 10.6 centimeters. Now, the other question that you might get in this sort of a situation is, let's say that we've been given that information, but what we really want to know is, how far is this distance right here? You should recognize that that's Pythagoras' theorem. It's a triangle. So we say a squared plus b squared equals c squared. This is 3 squared because it's centimeters, plus we don't know the short side, b squared equals, and then we have this number right here represents our hypotenuse, 100, 3 pi squared. And if I want b squared equals that number minus, because I'm moving the 3 squared to the other side, which is 9. And if I just wanted b, then I can take the square root of the whole thing. And if I wanted to 2 decimal places, it gives me 10.2 centimeters long. And that is surface area of pyramids and cones.